Welcome to the class of intelligent product design practices, and we are in the field of theory of inventive problem solving, in other words TIPS. And I have discussed till the last lecture up to principle 10. So, today I would go to the next principle in terms of bringing novelty to your product or to your patent. So, this is principle number 11, and that principle is also known as beforehand cushion. So, beforehand cushioning, that is principle number 11. So, what does that mean, beforehand cushioning? Well, we know that every system has certain predictable possibilities of failure. Okay? Let us take an example like a fighter aircraft, or let us say first of all a normal aircraft. When you sit in a normal aircraft, you would always see that the air hostess is telling you that in case of emergency landing, what is it you have to do? That she is telling it, and also they will tell you that how you have to put on the mask in case of the high altitude, suddenly the doors open, etc. How you have to put on the oxygen mask. All these things that the air hostess say and all these things that are kept are keeping in mind that the flight is inherently hazardous or dangerous. So, if the danger comes, what you have to do is arranged beforehand. Something very similar you will see in your car also. In a high velocity car, for highways, you would see that there will be airbag system. So, that in case there is a collision, then the airbag will come and save you, that your head is not going to bang on the neck seat or on the car structure. So, this is a beforehand cushioning system. Now, for the fighter aircraft I was telling you, there the way they do it is that because it is at a even higher velocity and you will get a even less time. So, the entire seat ejects out with a parachute. So, you do not wait till the pilot puts on the parachute, then comes out, jumps, etc. You do not get all those times. It is a split second decision. So, the beforehand cushioning is even faster there, that a simple ejection switch, if you press, it is going to take you out of the system. That is how beforehand cushioning is a very important principle that has to be utilized for any complex system design. So, we call it as prepare emergency means beforehand to compensate for the relatively low reliability of an object. Now, there are plenty of examples. I have only talked about some simple examples, but you think of it that the magnetic strip on photographic film was used for, today of course, digital technology is not needed, was used for beforehand cushioning. The backup parachute example I already told you. Dual channel control system in terms of controlling an aircraft, mostly a trainer aircraft, that is for beforehand cushioning. Airbag I told you, spare wheel, all things spares, including the the spare systems that is provided in automobiles. So, that is there. Relief valve, emergency lighting circuit, battery backup, automatic saving operations performed by computer programs, auto save after certain number of minutes, zip files, mask borders of objects to be painted using stencil, so that in case of the paint overshoots, it is not going to create any problem. Crash barriers on motorways, touchdown bearing in magnetic bearing system, multiple hydraulic systems, and then the puncture avoidance fluid, which is so popular, the slime puncture avoidance fluid. These are all examples of beforehand cushioning of a system. So, which is very heavily used. So, we have so many applications I could show you. Principle 12 is interesting, and it is a little bit more complex or less common sense than the other principles that I have discussed. principle 12 is equipotentiality. What does the equipotentiality means? It means that you would always or you should always prefer to work in a surrounding where there will be least change of potential energy required. To tell you very simply, you would certainly not like to do some work which involves doing some work in the ground floor and then jumping up to first floor, coming back to second floor. It is a much more energy consuming process. Many of you might be actually, you might have seen how typically a car or any such a bus, how they are maintained. They will either dug a small hole so that the person who is going to clean up the chassis, inspect the chassis, can go inside and then see the car, or they will have a hydraulic jack system which will lift the entire thing up and then they will do the cleaning and everything. All these things are done in a way so that you can maintain the equipotentiality. So, if an object has to be raised or lowered, redesign the object's environment. So, the need to raise or lower is eliminated as far as possible and or try to do it through the environment redesign. So, all these things, a beautiful example is the canal locks, which is not so much used today, but for the canal based transportation, let's say the Panama Canal, if you see, then you would see that there are a lot of slope changes, and the way they do is that a ship comes to a particular point, then they lock the downstream and then they increase water. So, because of hydraulic pressure, the ship also starts to go up. Once it reaches the perfect level with the next level of water, then the next upstream lock goes down and then the car moves or the ship moves. That is the way the canal locks beautifully work. You look into YouTube, Panama Canal movement, etc., you would see such canal locks. Spring loaded parts delivery system in a factory. Mechanics pit I already told you. Place a heavy object on ice and let ice melt in order to lower it. Angle poise lamp, changes in gravitational potential stored in balancing springs. Descending cable cars balance the weight of ascending cars, that is used both for elevators as well as for ropeways. So, these are all principles of equipotentiality. Now, we come to a principle which is very much used in terms of solving a design problem when you cannot do it through a forward manner. We call this principle as the principle of the other way round. And what it simply means, there are three connotations of course. The first one is the most important one. What it means is that invert the actions used to solve the problem. Example, instead of cooling an object, heat it. To loosen the stuck parts, we generally cool the inner part instead of heating the outer part. So, that way you can release it. Or the vacuum casting, or say the test pressure vessel by varying pressure outside rather than inside the vessel, or let us say place nuts in a vacuum to get them out of their shells. So, everywhere you actually invert the problem. Okay. So, let us say you have two systems to actually move relatively against one another. If the traditional mechanism is to move system A, then you try to hold the system A and try to move system B. So, that is inverting the action. Then make movable parts or the external environment fixed and fixed parts movable. So, once again wind tunnel is possibly the best example of it, because in wind tunnel what do? We basically place a system, let us say an aircraft, and then instead of the aircraft flying at a high speed and you are checking how the vortices are developed, instead of that the aircraft remains stationary, you let the wind move at a very high speed, and it is the question of a relative velocity. So, that you would be able to make out that how much are the changes. So, make the movable parts fixed and fixed parts movable. Finally, another connotation is turn the object or the process upside down, like let us say clean bottles by inverting and injecting water from below, then the water then drains by itself. So, you do not have to spend extra energy for draining, or turn an assembly upside down to insert the fasteners, or open tin bins from the bottom to get out bins that would otherwise have stuck to the bottom due to storage. So, this is something that you will not see in too many applications, but it is a better idea to release the items from a packaged system. So, this is what is the other way round. Now, let us go to the next principle, principle number 14. I have talked about this principle, if you remember, while discussing about the stacking of the bottles, cold drinks, etc. So, this principle is all about spheroidality or curvature. Spheroidality is a special type of curvature, but you can think of other curvatures like positive curvature or negative curvature, need not be always spheroidal, it can be parabolic, it can be hyperbolic. So, use of curvature is the key thing in this principle. Instead of using, so first clause in that is, instead of using rectilinear parts, surfaces or forms, use curvilinear ones. Move from flat surface to spherical ones, from parts shaped as a cube, parallel pipette to ball shaped structure. For example, use arches and domes. I think for a very long time, till before Christ, if you see the discovery of arches, by the way, that has happened in our own country. In the Indus Valley civilization, people used something which is called corbelled arch, by sort of placing the bricks one ahead of the other, they created the curve structure. So, something like this. So, this is the first phase of creating curvature in a construction, which later on people have been able to do it with a nice curved parabolic kind of structure. So, uses of arches and domes are the use of the curvature. And what was the advantage in that case for going for curvature is because you can then keep the system predominantly compressive in nature, and compressive systems are good as far as stones and bricks are concerned, because they have a higher compressive strength than the tensile strength. So, it has been used for making such structures which can predominantly carry compression. Similarly, introduce stress relieving holes at the ends of slots, that you might have seen that in any slot, let us say if you have such slots there, then there is a chance of cracks propagating. So, you keep such kind of small holes that will deflect the crack, and then change curvature or lengths to alter the deflection properties. Now, other examples could be use of rollers, balls, spirals and domes, like the spiral gear, or use of spherical casters, or the famous screw called Archimedes screw. So, these are all use of rollers, balls, spirals. Okay. And then another group is go from, so that is use of roller balls. So, next is go from linear motion to rotary motion, or vice versa. So, the rotary actuators, or switch from reciprocating to rotary pump, linear motors, these are such examples. And then use of centrifugal forces, that is also related to spheroidality or curvature, because the centrifugal forces are generated because of the motion in a spherical or a circular motion system. So, that is how principle 14 is used in many different cases. Principle 15 talks about dynamics, and there are again, dynamics is a very vast principle. There are again 4 different dynamics principles. Principle A in dynamics is allow or design the characteristics of an object, external environment or process to change to be optimal, or to find an optimal operating condition. So, that means unless you have a certain bit of dynamics that you allow in the system, you won't be able to set the system in its optimal location. Okay. So, a very simple thing that I can tell you is that you think of a locking mechanism. Okay. Unless you have some such locking system and you have a sort of a ball, let us say paste system which is to be locked. Now, if you clip this little dynamics, it will slide and it will come to this part, okay, and you can have a special slot here, so that it goes inside. So, that is the way if you do it, then you are using the system dynamics to lock two systems. So, this is something which is very much used in all your turn indicator mechanisms of automobiles. Similarly, dynamics is used in shape memory alloys or polymers, racing car suspensions, adjustability, telescopic curtain rail allows one size fits all. So, these are all allowing certain dynamics to happen. Secondly, so this is allowing the characteristics of an object. Secondly, divide an object into parts capable of movement relative to each other. For example, a folding chair. So, you are playing with the dynamics that you can actually deploy it as and when required. Okay. Brass seals. So, there are many such examples of dividing the objects into parts. Then, if an object or process is rigid or inflexible, make it movable or adaptive. Like you have a joint which can move, but it is inflexible. So, create a flexible joint or create a streamer. So, this kind of things actually would allow optimal placement, optimal positionings, versatility of the system, etc. So, that is use of some additional dynamics to make a rigid system movable. Increase the degree of free motion. Suppose the system is originally we measure this in terms of degree of freedom. System is having 1 degree of freedom, you add additional DOF like 2 DOF, 3 DOFs, etc. So, that is another way in terms of introducing dynamics in the system. Now, I come to the next one, that is principle 16, which talks about partial or excessive actions. So, many a times we say that an action will be over once when I do the 100% of it, but that should not be the case. That may take enormous amount of time. Rather, we should go for 90% or 110%, and then for the last part of it we should allow some special way of doing, so that it becomes a much more accurate yet faster way of doing something. So, if 100% of an object is hard to achieve using a given solution, then by using slightly less or slightly more of the same method, the problem may be much faster, you may solve it. Okay. One example I tell you. See, if I draw a circle in the screen, okay, it may not be a perfect circle, does not matter. I am just trying to tell you about the idea. Okay. Let us say I have done this. Now, in your eyes it is looking like a circle or a curve, but actually what is happening here is that there are very small pixels that are basically drawing this entire system in this kind of a way. That means, it is neither drawing a full circle, nor it is drawing a kind of a a complete straight line, but it is a kind of a slightly more or slightly less of the area type of a principle. So, this is what is one of the way the digital systems in computers they operate. So, similar things you would see people adopt when they overspray a painting, because it is much easier to do it and keep some mask. Okay. And there are other things also, like shrink wrapping process uses plastic deformation. Okay, roughing and finishing in the machining operations. Okay, you make a particular cut fast and then you finish it up. Okay. So, like that the partial or excessive action is taken care of. Principle 17 is interesting. Principle 17 focuses on adding further dimension, and that is extremely useful in terms of making a system compact. See, that is why so many examples of it. The first group of example is that if an object contains or moves in a straight line, consider use of dimensions or movement outside the line, so that you are adding another dimension. Okay? For example, you coil a telephone cable, so that you can, it will remain smaller, compact, but whenever needed a person can extend it to a much larger distance. Or curved bristles on a brush, you are adding a dimension extra. If an object contains or moves in a plane, consider use of dimension or movement outside the current plane. That means add an extra plane. A spiral staircase which uses less floor area. Introduction of down and up slopes between stations on railway reduces strain, acceleration and deceleration due to power requirements. Or conical instead of plane flange joint. Use a multi-story arrangement of objects instead of a single story arrangement, like a cassette with 6 CDs to increase the music time and variety. Multi-story office itself, multi-story block or something. That means instead of horizontally growing, you are adding the third dimension. Tilt or reorient the object, lay it on its side like a dumping truck, what you call it. Use another side of a given area. Mount computer chip components on both sides of a silicon card. We have used this in a very interesting example that I have shown you in the first day or second day itself. As I told you that we had to develop a kind of a linear actuator, right? And if you remember that it had a bipennate actuation system like this, and there is some spring here, and it is supposed to pull some load here. What we figured out is that this is a plane, but the other side of the plane is not utilized, that means this side. So, we started adding a similar type of bipennate actuators on this surface as well, the back side of it. So, that way we can increase the pulling power of the system, we can actually make it double. Now, I come to principle 18, which is of mechanical vibration. In this case, we would like to use the vibration in order to do some work, like cause an object to oscillate or vibrate. You see, all this electric carving knife is based on the principle of vibration, or a hammer drill, or vibration used during the sieving operation. So, create an oscillation or vibration. So, that is one. Suppose the entire thing is already vibrating, you increase its frequency even up to the ultrasonic. So, ultrasonic cleaning is one of the example of it, or non-destructive crack detection using ultrasonics. So, increase the frequency. Use an object's resonant frequency in order to do some work, like say destroy a gallstone or a kidney stone, or ease the bottle cleaning by pulsing washing action at resonant frequency. Then use piezoelectric vibrators instead of mechanical ones. So, that would become an electromechanical system, because we know that piezoelectric materials are like smart materials for which the electric field change can create a mechanical change, like a change of displacement or change of force. So, using that you can actually create a vibration and maintain it electrically. Use combined ultrasonic and electromagnetic field oscillation, two different type of stimulus together to generate vibration, like mixing alloys in an induction furnace or ultrasonic drying of films. So, these are all mechanical vibration principles. I now come to principle 19, which is the principle, you may think it is almost the same as vibration, but periodic action is not exactly like vibration. Okay? So, periodic action in that sense may mean some signal which is not vibration, but at least it is periodic in nature. Like, let us say that a vibration signal can be something like this, but loosely speaking a periodic signal is something like this. So, there is an element of periodicity or something like this. This is called a sawtooth signal. So, use of such periodic signal. So, now the principle here is that instead of continuous action, use periodic or pulsating action, like hitting something repeatedly with a hammer. If you have to drive a nail, instead of putting all the force in one shot, if you use a small force, but do it continuously, that way you would need less force, because that continuous periodic excitation will actually create certain crack generation, and then the structure that you are trying to insert will go much easier, in a much easier way. Exactly the same strategy people use for pile drivers and hammer drills. Replace a continuous siren with a pulsed sound or pulsed bicycle lights that make cyclists more noticeable to drivers, no? If it is pulsating. Pulsed vacuum cleaner suction, pulsed water jet cutting, okay. Pulsed we have PWM signals for stepper motors. So, this is example of, instead of continuous action, you have pulsating action. If an action is already periodic, change the periodic magnitude or frequency. So, something like washing machine or dishwasher water injection, that operates all these different type of cycle loads. Then earlier generation, the Morse code, the dot and dash, you can change the magnitude. You can use AM, FM, PWM, I already told you. So, these are already periodic, but change the periodic magnitude and frequency. Use pauses between actions to perform a different action, like inkjet printer cleans heads between passes, or brush between suction pulses in vacuum cleaner, or multiple conversations that take place in the same telephone transmission line, or use of energy storage means, right, like batteries, flywheels, etc. So, these are the examples of periodic action. Now, I come to continuity of useful action. If an action is already useful, then you try to continue that action without stopping it. That means, make all parts of an object work at full load or optimum efficiency. It always comes in my mind that the diesel engine would generally never stop, because if it stops, then you will need much more energy to start it back again. So, you will always see that in a station, the diesel engine, even if the train is waiting, diesel engine is not stopping, it is continuously there. Similarly, flywheel stores energy when a vehicle stops. Okay. So, continuity of useful action. Constant output gas turbine in hybrid car, constant speed variable pitch propeller, self tuning engine, okay, heart pacemaker. So, these are some of the examples. The second one is eliminate all idle or intermittent actions of work, like say self cleaning, self emptying filter eliminates a downtime. Print during the return of a printer cartridge, dot matrix printer uses it, or daisy wheel printers. Digital storage media allow instant information access, or kayaks, for example, that use double ended paddle to utilize the recovery stroke also. Computer operating systems utilize idle periods to perform necessary housekeeping tasks, or the rapid drying paint. Okay. So, continuity of useful action is a very important principle. So, I have talked about up to 20 principles in this lecture, and in the next few lectures we will talk about some more TRIZ principles, and then we will talk about how to utilize these TRIZ principles. If you remember that we had these 39 engineering parameters, right. So, 39 EPs, and I told you that any contradiction, let us say between engineering parameter 1 and engineering parameter 5, you will see in a matrix form in which we will have in this side all the technical parameters, and again in this side the technical parameters, and then in this matrix we will talk about that what are the principles that are utilized for all of them, and that way we will see all the principles that we are now first going through, how they are used in terms of solving different technical contradictions. That is the way we will do it, and let us stay tuned till the next class and the class after that in order to learn TRIZ completely. Thank you.